Welcome back. So let me introduce you to this idea called transfer learning. So you recall that neural networks are functions, right? So given data x in RD, let's say that you also have y in R. It doesn't matter if it's supervised or unsupervised. You have this. Suppose we learn a neural network. Suppose so G phi is a neural network from RD to, or rather x to y, is a neural network learned via ERM. Okay. Now there is some task and we have trained a neural network and learned it. Okay. Now recall that a neural network is a composite function, right? It's a composite functions of linear and nonlinear transformations. So you can tap the output of the neural network at any of the compositions. What do I mean by that? So since G phi is a composite function, the outputs can be tapped at any layer. Okay. Now I will define Z to be G phi of x, okay, at layer L. I can do this, write this as G phi star, denoting that star is the set of parameters that you have gotten after performing ERM. Of course, yeah, ERM is training. After you train, you get a set of parameters. That's what I am indicating by G star. Now Z can be the output that we have obtained on data at the Lth layer of the neural network, and this L can be anything. Okay, and this is typically referred to as the embedding of X. Okay, from G star. You might have heard of these terms, right? BERT embedding. This is exactly what is done. So BERT is a particular architecture that is trained for a particular task. Now you train that, okay, and by the way, this G star, okay, is also called as a pre-trained neural network. And the standard libraries today will give you the parameters of neural networks that are pre-trained on several data sets and tasks. So this is a pre-trained neural network. Now what do you do with a pre-trained neural network? You can tap the output of the pre-trained neural network at any intermediate layer, okay, for a given data, and do what with it? You can use Z for any further downstream tasks. It can be supervised, unsupervised. Think of Z as a feature that you have extracted from that neural network and use it for any downstream task. Okay. Now this is one form of embedding extraction and transfer learning. Typically this is not what people refer to as transfer learning. Okay, any questions on this so far? Yeah.
Like when we are using any feature for the downstream task, how do we understand that which layer or which feature?
That's a hyperparameter. So for instance, I think one particular layer of ImageNet, InceptionNet trained on ImageNet data set is taken to compute a metric called FID, Freshet's inception distance. Okay, so now how did they come up with that particular layer? Is through experimentation. So they saw which feature corresponds to the human perception the most and took that particular layer. Okay, this is a hyperparameter. Okay, so now this also can transform your data. Let's say that you are using images, okay, can convert images into vectors. Okay, so why is this useful is because what happens is, even though the distributions are different, let's say that you are looking at two different data sets. Okay, one is the data set of uh, normal images, or rather free form images. The other is the data set of, let's say, a particular type of medical images or something. Even though these two data sets are being sampled from two different distributions, and IID assumption breaks if you do that, since these are both coming from the same image domain, perhaps the features that have been learned in the initial layers of the neural network that is trained on the free-form images are useful for the other domain as well. So what you do is that take the neural network that is pre-trained on the large-scale data set and tap the features from one of the earlier layers and then use it for the downstream tasks. So this is very similar to doing this, right? Let's say that we have this function g. So we have x and we have, this is g phi. This is layer L, and then we get z here, correct? This is all fixed, this is all freezed, and you are not training this. You can append another neural network here, which is some f theta on z, and perform ERM on f theta for your particular task. You get it, right? So this is what is typically referred to as transfer learning, where you're sort of transforming the learning, right? So you take the network that is pre-trained on some other data, append another neural network. When you do back propagation, how do you do this? The forward pass does not change. Toward, when you do the backward pass, you make the parameters of this neural network freeze, right, or non-trainable. You treat it as a fixed function. That's it. So it is like you have x that is being passed through a deterministic function g phi, and then you have a neural network on top of it. And all these standard libraries such as PyTorch will give you capabilities of freezing a particular layer. Okay, only train f theta. So this is transfer learning. When you do transfer learning, there's no hard and fast rule that you should freeze only a few. You should always freeze a few layers of the pre-trained neural network. You can take a pre-trained neural network, use that as an initializer, and train the entire neural network as well. You see what I mean? So why is this useful? Typically in a neural network, when you train, we know that that would be trained using gradient descent. Gradient descent is an iterative algorithm, and we need initialization. Random initialization is what is done typically. Okay, but now instead of doing a random initialization, it is better if you initialize the parameters to be the parameters of a neural network that is trained on a similar data set. So that in the parameter space, search space is always the parameter space. In the parameter space, you are already starting in a region which corresponds to some images, some useful distributional data, and from there you navigate whatever data that you need. That's also another way to do transfer learning. Is that okay? Yeah. In fact, one can do in this context, right? As I said, these can be used as Lego blocks. One can actually do what is called as multitask learning, where use the same set of features to do some classification here and some bounding box regression here and multiple tasks on the same set of features that are being learned. Now when you do back propagation, there is one path towards this task and there is one other path towards this task and so on. The only thing is the gradients will get added here before it goes to the input. That's it. So this paradigm is called multitask learning. In fact, you can do this from scratch as well, meaning you have a neural network. So basically there are two composite functions, okay, but initial compositions of these two functions are same. up to a few layers. That's it. You are learning two composite functions together using gradient descent. That's the idea. What is the intuition behind it? The intuition is that suppose you are solving two different tasks on the same data. The initial set of features that are to be learned to solve a particular task on the same set of data are the same. So you share the parameters across different tasks. That's all right. So this is about transfer learning and pre-training and multitask learning and so on, different paradigms of learning. Any questions on this?
Retraining which you told, are we actually learning the Z itself? Obviously, we're getting Z, but actually the parameters which are there in GP is the learning rate.
I didn't get the question.
Actually, when we say transfer learning, we are transferring the parameters. That is the actual learning which we get.
Well, you are transforming the parameters because the initial set of parameters are being transferred by not training them at all.
That is the learning.
Yeah, I mean you are doing learning on this is also a sort of regularizer, right? Out of 1000 parameters that are there, I'm saying 500 parameters are fixed to a particular value which is given by another neural network. That's it.
In backpropagation, freezing means not keeping track of gradient for pre-trained model.
Oh, okay. It depends on what layers do you freeze. Suppose you freeze layers, suppose you freeze some intermediate layers and try, I mean not freeze the earlier layers, then you have to keep track of those gradients because those gradients will be with respect to constant functions will be constant. You'll have to carry them through because if there are layers that are behind the layers that are frozen, then you have to remember the gradients. Otherwise, you don't have to remember the gradients. Depends upon what layers do you freeze. See here in the version that I wrote, all the layers between input and the representation is sort of frozen. You don't have to do that. You can freeze intermediate layers as well, which is seldom done. It's not often done. Typically, the some of the layers from the initial input to a few a particular layer in the neural network is what is frozen. In which case you don't have to see, you still have to get the inputs to get the final laws and the gradients, right? So yeah, it's a matter of detail. Anything else? Okay. So this is, see, in nowadays most of the ML tasks or neural networks are not trained from scratch. Okay, most of them are transfer learned because and okay, so one interesting question that I thought some of you would ask is as follows, right, which was not asked, is that I told you that this GPhi is trained on a supervised task. Now if it's trained on a supervised task, would the features, okay, so first of all one point is the kind of features that are learned or the transformation that is learned by GPhi is completely dependent on what sort of task it is being trained for. And we know that all supervised learning, the goal of all supervised learning in ERM is to estimate the posterior density of y given x. If we do a supervised, if we solve a supervised task, we are estimating p of y given x. Why should a composite function that estimates p of y given x be good on some other task where y does not exist? Nobody asked that question. That's actually pretty important. In fact, in most of transfer learning, this GPhi is not trained to estimate p of y given x. This GPhi is trained to estimate the marginal px. See, all methods that are designed to estimate marginal px are called unsupervised learning methods. We will see examples of some of it later in the course. One example can be that you have a neural network that would simply reconstruct the data back or denoise the data. Start from x, okay, add some noise to data and the task of the neural network is to estimate px from px cap, where x cap is the perturbed version of x. That's called auto encoding. We will see examples of it later. So those kinds of neural networks are the ones that are used as feature extractors for transfer learning, because you are estimating it only is very natural, right? If you have a method that would estimate the marginal, then you can perhaps use some of its features to solve the conditional tasks. But if the neural network that is that is built to estimate the conditional distribution, you can't use it for the other kind of conditional distributions. Therefore, most of the backbone or the embedding extractors are trained on an unsupervised learning task, which is equivalent to saying that they are trying to estimate the marginal distributions. And there are multiple ways of doing it. One way of doing it is, as I said, perturb the data, right, and ask it to denoise the data. So that is called masked encoding, right. So you just take a sentence, take a sequence, remove some of the tokens and ask your neural network to predict those tokens, fill in the blanks, or give it t minus 1 tokens, ask it to predict the next token. That is the autoregressive way of doing it, and that is exactly how the modern day LLMs are trained. Okay. So there is another learning paradigm where a pre-trained neural network is used, okay, which is called knowledge distillation.
So the ImageNet was trained on which task? That is
Self-supervised tasks, which is that there are multiple tasks on which it was trained. One was that you rotate the image and predict the angle of rotation. Okay, you mask the image and predict the mask pixels and so on. Perhaps it's a good idea to talk about self-supervised learning as a paradigm in this course. I'll do that later in one of the classes. I'll spend some time on self-supervised learning techniques. Now, after unsupervised learning, we'll do self-supervised learning as well, because most of the modern day ML is done in a self-supervised manner. And by the way, another side remark here, I told you that all the methods that are designed to estimate the marginal distribution can be used as feature extractors, right? All generative models by definition are marginal distribution estimators, and that is why all generative models, the positive side effect of all generative models is that they are also embedding extractors. So I will show you this mathematically in my next course, right, when I talk about generative models, marginal estimators, all of them are embedding extractors. Okay. Okay, so let us look at the idea of knowledge distillation. I will only talk about the empirical way of doing knowledge distillation, but there is a very nice Bayesian framework on why this should work and so on. Again, I will do it in my next course. The idea is as follows. So suppose there is some data, again x comma y, that is sampled from pxy, and a neural network G phi is trained on a task. Now let f theta be another neural network So typically with lesser parameters than G phi. This is a typical case, but the theory does not stop you from using another neural network with arbitrary number of parameters. So we have two neural networks, one is G phi and the other is f theta. Typically f theta will have lesser number of parameters, much lesser number of parameters compared to G phi, and this is referred to as the teacher network, and this student network. Student will have lesser number of parameters compared to a teacher. Typically, right? So there are exceptions always. Okay, yeah. So what's the task here? The task is, why do we do this? Most of the cases knowledge distillation is done because you want to imbibe the knowledge that is in the teacher network onto the student network. By the way, this was actually proposed by Geoffrey Hinton in 2012. The math followed later. It was a very nice math in terms of Bayesian Uh, okay, I'll just tell you what it is doing in a while. So the reason we do this is that suppose you have a very large neural network, okay, and you have a hardware which cannot support that large neural network. You want a neural network that is smaller in size but have a similar performance as that of the larger neural network. What do? Is that you construct another neural network f theta, which is a student neural network, and suppose you have access to some data or some samples from pxy. What you can do is simply do an ERM on f theta, right? Because you have access to data, do ERM on f theta. But however, this may not give you performance that is as good as a teacher network, because teacher network is one, larger in number of parameters, and two, it has seen more data compared to the student network. Now the question here is, now how to get the performance of the student network to match that of the teacher. Right, with this question there was these class of methods called distillation, knowledge distillation, that came. Okay, so how is it done is as follows. So let us say that typically in most cases teacher network is not trainable. Okay, so the parameters of the teacher network are fixed. You have this g phi star, and you have a smaller student network f theta, and we have access to sum of the y. So what is done is as follows. So you tap the output of the teacher network at some layer. This is pre-trained from lth layer. Okay, and now you take the lth layer. Let's call this zt. This is zs. Zs is the output of the student network at the lth layer. Now ensure that the dimensionality of zt is same as that of zs. See, have you noticed this? If you misspell something and write it, it visually looks something bad. Have you noticed this? See, what I mean to say is, I just missed this n. Okay, I wrote it as this. You don't even have to read the misspelled word. You have a visual feedback that would say that this is wrong. Have you noticed that? Exactly. So some internal representation that the teacher network has already done, right? Which not even auditory. I'm just saying the visual representation is completely gone. You have to go back and see what was the mistake then, right? You don't have to even read. I mean, the very first visual feedback will tell you that this is wrong. Anyway, so ensure that these dimensions are the same. Now, what is done is, while you train the training objective or training of rather I will write it the other way around. So regularize the teacher network, or sorry, the student network such that the expected divergence, okay, between the distribution of zt and the distribution of zs is minimized. Okay, take the expectation out. You understand? Now the zt is a random variable, right? Because we are sampling x from the distribution, the neural networks, and okay. By the way, one other point to be made, I don't know if you noticed this or not. Neural networks are deterministic functions. What do I mean by that? Once it is trained, okay, they give you the exact same output given a particular input. There is no stochasticity associated with it. Okay. The only source of stochasticity is in the data. Neural networks are deterministic functions. Remember this. There is no sampling with, there is no stochasticity associated with neural networks. Now, what am I saying is, since neural networks are deterministic functions and x is a random variable, when you pass it through the neural network, if you tap the embedding at some else layer, that also is a random variable which has a particular distribution, because it is a function, deterministic function of a random variable that has a distribution PZT, and this will have a distribution PZS, right. Now, what am I saying is that while I train the student network, I am regularizing the distribution of PZS to be the same as that of distribution of PZT. What is the objective here? What is the intuition here? The intuition is that whatever feature that this teacher network is learning at layer L has to match with the features that the student network is learning at layer L. Now, how do we use this? How do we calculate this divergence metric between these two distributions? Again, using statistical methods. Assume some distributional form on this. If you assume both of them to be normally distributed, then KL divergence between these two will become the squared error. If you have two random variables that are normally distributed with 0 mean and unit variance, if you assume them to be having a particular distribution, then KL divergence is simply a squared error loss. So, you just add this additional squared error loss while you are training the student network. So, the empirical risk for the student network will be, so minimize, so I have to get our theta, that would minimize this divergence between PZT and PZS plus the usual empirical risk or the usual loss function that we define on the student. The second term is simply the supervised training, right. The first term is called the teacher matching term, where you match the distributions of the representations that the teacher has learned and the one that the student is learning. Do you see that as regularization? We are not regularizing in the parameter space, we are regularizing on the activation space or the embedding space. And I told you, right, regularization can be done either on the parameter space or on the activation space and so on. This is a type of regularization, but the regularization is coming from the distribution of the teacher. Okay. Now, today in the commercial world, when a company releases LLMs, they release LLMs of different sizes. So, there is 100 billion parameter model, there is 170 billion parameter, 30 billion parameter and so on, right. These smaller models are the distilled version of the larger models. Okay. Distillation comes with a catch. The catch is that it will degrade the performance because the number of parameters in the student is lesser, but you will have to deal with it. I mean, the hope is that while you distill, the performance is not degrading, but it will always, because the number of parameters are much lesser compared to the student network, the teacher network. And what is it doing mathematically is that there is and why should this work? It can actually be theoretically shown that this entire process is actually minimizing the KL divergence between the true posterior that we would want to minimize, okay, and a posterior by assuming that there is label noise. Don't worry about it, I will do it in detail in my next course, but yeah. So, there is a very nice, when Hinton first came up with this idea, this divergence was called as dark knowledge, okay. And but in 2021 there is a paper that came that analyzed this, and it talked about the title of the paper is a Bayesian framework on distillation, where they give theoretical reasons so as to why this thing is actually working, but yeah, empirically this is what it is. All the smaller models that you see today are the distilled ones, okay. And this can be done for any task, as you can see, right. You can distill a CNN, you can distill an RNN, you can distill a transformer or an MLP or anything, doesn't matter, yeah. All these are architecture agnostic. Any questions on this?
free LLMs that are there, they are student networks.
Come
Free
again.
versions of many of
One will be teacher, the other will be students. In fact, I should not be saying this on camera, but the thing is, there have been accusations that one particular geography uses the LLMs trained by another geography and distill them. You are not supposed to do that. I mean, when you sign the user agreement, most of these LLM providers will make you sign, will make you agree to the fact that you will not be using their inference to do anything further. Okay, but yeah. And please note that if you were to distill, there should be a way to tap the output from the intermediate layers of the teacher network, which may not be the case always. Commercially available LLMs will only show you the final output, right, not the intermediate output. So distilling is not easy, so to speak, but you can use some RL techniques to do that as well. Okay.
Is this applied to only one layer in the teacher model?
Good question. Not necessarily. You can distill multiple layers. The question is, can the distillation be applied to multiple layers? Yes, it can be applied to multiple layers.
Stand into the K level.
Yes, yes, as different KL divergences. In fact, in one of my R work, we have shown that doing it at multiple layers will give some performance boost, and we also have theory associated with it.
So is there any restriction for the student and teacher to have similar architecture?
Not necessarily, but at least the question is, should the architecture be the same? Need not be, but for this distribution to be computable, you need the dimensionality of those to be same, right? If you have two different random variables which are supported on two different spaces, you can't compute divergences, right? That's okay, right? That's a hyperparameter choice. You anyway make it to be equal. That's it. Yeah.
Will the digital model always have degraded performance or sometimes it will have boosted?
Yeah, depends upon the parameters. You know, there are distillation techniques where teacher and the student network may have more parameters compared to the student network. As I said, theoretically speaking, these are all, I mean, there is no restriction so as to why the student has to be smaller, having smaller parameters. That can happen. Distillation may actually increase the performance. Yeah. Yeah.
JDS must be the final layer of the student.
No, it need not be. Some intermediate layer of it need not be. It's always not the final layer typically, because if you are solving a supervised task, then the final layer has to be the label, right? It should be softmax if you are solving a 10, let's say 10 class classification problem and so on. Yeah.
Sir, since L is in any arbitrary layer and dimensions should be same, so how exactly the perimeter student network is less?
Why not? See, you can use, let's say that X is 100 dimensional, right? I have 100 layers here. I only have 50 layers here, and I make the 45th layer to be having the same dimension as that of the
Layer
student.
does not have to be the same, right?
Number of layers need not be the same. Only thing is, whatever layer you are distilling, whatever features you are distilling, they have to have same dimensions, no? Otherwise, the KL
Before that, after that, is
doesn't matter. Doesn't matter. Yeah. Typically, distillation when it is done at the layer of logits, which is pre softmax. You are solving a classification task. There's one layer after which you put a softmax to make it bounded between 0 and 1, right? Just before the softmax, and that's called logits. In the community, you distill the logits in most of the cases, but there's no restriction. You can do it at any layer. You had a question. Yeah. Not necessarily, but whatever layers you are distilling have to have the same dimensionality. That's it. The math will go through, right? I mean, the only thing is the divergence metric has to be computable, and if that has to be computable, the random variables have to be supported on the same space. As long as that is happening, it doesn't matter. Okay, fine.
we said that for estimating this, we for estimating PZS, we sample we sample some samples from the training data of the
Sample some samples. One is a verb, the other is a noun. Yeah.
from the original training data of the teacher model.
Correct. Both. You have to do it both. So you take some data, do a forward pass through the pre-trained teacher network, collect a few ZTs, and use the same data. You have to use the same data, and pass it through the student, do a forward pass through the student network, collect ZS, and then do one batch of backprop and update the parameters. Repeat it iteratively and do the same thing with the student network again, sorry, teacher network again, get the new set of, that won't change, you can store it, right. But if you do one backward pass through the student network, the parameters changes, so ZS changes. So you recompute the divergence, back propagate, and multiple iterations is what you do.
So my question was, if we were to train a model of the same size as that of the student model, and it is trained on all the samples that the teacher model was trained on, but its parameter size is less, which would perform better out there?
Depends on the task. Question is a good question, right? Theory wise, what can be said is, yeah, the question is, if you make the student and teacher the same size and let's say distill, will the student do better than teacher, right? Was that the question? Yeah. That paper that I mentioned, right, actually says that if you distill with the same size, the distill model will do better because it encompasses the label noise is the climb. Okay, and empirically most of the cases you can actually see that. So distillation can be used as a way to regularize. Okay.
Both must have the same task.
Both must have the same task also is not necessary. You can train the teacher to estimate the marginal, and you can use the student to estimate the conditional as well. Doesn't matter. That is also a possibility. Yeah. Dark art elucidates a lot of questions, right? Oh, one more question. Okay. Oh yeah. Yeah. Can teacher and students be of different they will be of different architectures, right? Or, I mean, are you saying that one is a CN and the other is an MLP or something? Yeah, yeah. I mean, no restrictions have been put here. Okay. Okay, so this is about distillation. So now we'll do the last piece that I wanted to talk about today, which is training neural networks with adaptive learning rate. We will stop here and continue in the next lecture.